My name is Patrick Morgan. I'm a developer at Tag Creative Studio, and I helped work on Yeti Bowl, which is the project we're going to be showing you today, built entirely in HTML5 and then ported over to a Windows 8 app. And let's see. So let me give you a little bit of background on myself first. I'm a game developer, and I've been a game developer for several years now, but I've been building games since I was probably in 3rd grade, back when they used to provide tool sets with every game that came out. So I don't know if you guys remember the old Load Runner games or Warcraft 2, but more recently I've been building a lot of games in HTML5. We released Newton for the Windows Store, and Yeti Bowl is our second major project in HTML5. The version we'll be showing you today is a much more basic version than what we eventually built it into, but it shows you a lot of the systems that you can build in HTML5 and what you can expect from the earlier stages of the project. So let me show you the game first, actually. So the game is pretty simple. You are a Yeti at the top of a mountain, and you have a snowball with which you knock all of the hikers off the mountain. This is all built in HTML5, and I'm running it in the browser right now. So, without further ado, let's talk about how to build this. Today we're going to talk about how to build a game starting from scratch. So we take HTML5, which is extremely flexible, and use both the document object model for building out the UI and the game system, as well as sort of an MVC pattern to build out the actual game engine behind it. We'll set up the basic objects we need for the game structure in JavaScript, and then we'll start drawing them on the HTML5 canvas element. Then we'll talk about what makes up the game loop, the most important part of building your game. So how do games work? Games run in what's called a game loop that constantly updates the state of the game and draws that current state, the scene, to the canvas. Each iteration of the loop is called a scene, and when we draw that scene to the screen, we call that a frame. So it's very parallel to a cartoon animation, where each drawing is a camera frame, or like a child's flip book, where the illustration is redrawn in a slightly different place, and in flipping it, it looks like it's animated. To start off, the canvas element is a new HTML5 element that allows you to render images and shapes to the screen. If you've worked in any other languages, it's very similar to those kind of canvas elements. It's the foundational element of an HTML5 game, and it allows you to draw programmatically with JavaScript. Also, it's hardware accelerated in IE and Windows 8, so it's what makes games possible in HTML5. The canvas is a 2D grid, and so you can draw objects to it by passing them in coordinates. It's really important to note that the top left corner is position 0, 0. So that's what's going to be your anchor point from which you draw everything. Games are built generally out of a very basic page structure, so you're not going to be spending too much time building it in the DOM. For Yeti Bowl, we use a overarching container element, and that's scaled at runtime to give it proper aspect ratio as well as letterboxing. Inside the container element is the game canvas, and the width and height of the game canvas are set to the viewport size. That way, as the container scales, the game canvas scales with it. At the bottom of the screen is the snowball button, And that's just a simple button or div element that gets click events, and then passes those on-click events into the game logic. And that's also scaled with a CSS style. So in our system, game objects are either drawn by the canvas or the DOM. Items that are static, such as the sky background, we draw only once in the DOM for better performance, and anything that changes, like the Yeti or the mountain or the hikers, those are drawn on the canvas itself. Here's a code sample for the DOM. The parent element of everything is the container, and then inside of that is the canvas, which we give a static width and height, and the snowball button, which we pass an on-click event through. This is the CSS we use to scale images on the screen. So the top option scales up or down. The bottom option will use the 768 by 1366 as its smallest resolution. In this case, we'll use the top option and a JavaScript solution for those browsers who don't support this feature. So all systems in our games have an initialize, update, and draw method. The JavaScript construction can be broken down into these three, and we'll get a lot more into this later in this deck and the second deck, but it's key to point out that JavaScript loops through the logic and determines what is drawn on each screen of the frame. So the first part is initializing. When we initialize every game object, we load it into memory and grab whatever media, sounds, images are associated with it. And it's important to do this early so that you're not allocating memory while the game is actually running, because it's an extremely performance-intensive task. Once the object is initialized, we sorry about that. We can update it, which is any of its movement or one second, I'm going to get back to that slide. Any of its movement, collision data, any kind of changes to that entity. And then the draw section is where we actually take the media image and render it to the canvas element. So this is how you draw an image to a canvas. First of all, you have to load the image file, and then you set the source of your image to whatever the file itself is. So you want to make sure that the image is completely loaded before attempting to draw it, otherwise nothing will be drawn to the screen. So HTML5 provides the complete property for images, or the complete property. This will be set to true when the image is finished loading. You can also use the onLoad event to determine when an image is loaded. So we have a function here where after onLoad it will draw it to the canvas. So now that you have an image to draw, we need to draw it to the canvas. First we have to get the context property of the canvas, and the properties of context determine how objects are drawn to the canvas and provides methods to draw images and shapes to the canvas. There's no 3D context yet for the canvas tag. Everything is drawn in the same 2D context. So in this case we point a reference to it because we are going to use it a lot. With the context element, we can draw an image using the drawImage method. The image parameter is an HTML image element, which is our snowball.ping. the source is the location and the size of the image to draw, and the destination is the location and size to draw on the canvas. So you can see from this diagram that we're drawing at 100 pixels down and 50 pixels to the left, and the source image is 250 pixels wide and 261 pixels tall. So this is what the game loop looks like. The main game loop is the top level of the game. The class structure is start with initialization, then update, and finally draw, and then move back to update again. And we'll talk a lot more about this, especially towards the end of this presentation, and we'll go into actually what the code for this whole sequence looks like. Usually, the games I've worked in, the way every tick updates, or the tick is kind of the time between each frame. You start the next tick as soon as the previous one has finished, and so the time you're passing in between frames is the time passed. However, with HTML5 games, we find that it's best to use a set interval. So instead of just firing it off as soon as you're done with the previous, set an interval between each frame and then wait until that interval is passed. This means that you get a very reliable spacing between each, and it also means that since your update is separated from your draw call, you can draw faster than you update. So you might run an update loop only once every 3 draws, and so you might end up drawing at 60 frames per second even though your game logic is only updating 20 frames per second. This is called a fixed game tick, and we set the desired tick rate at 30 updates per second in Yeti Bowl, and then run an update whenever at least that amount of time has passed. So if enough time has passed where we need to do more than one update to catch up, we skip doing a draw to save time. This allows updates to catch up by skipping draw frames, and less updates are needed. It allows more consistent behavior overall. It's also really good for physics engines, because if you have a predictable amount of time between each physics engine update, then there's never any really quirky behaviors where like the snowball shoots off the screen because a full second took place in between each update. Since after the update logic, our game is now at the current time, the draw logic simply requests a frame to be drawn using the request animation frame API. The run function is now complete, and we start at the next iteration of the loop. Request animation frame is one of the HTML5 API calls used in the game's draw function. There are a couple other methods, but this seems to be the most performant option for requesting new frames. The request, mainly because the request API allows the OS to optimize the draw to be sort of optimal rate based on the user's machine. We pass this our draw function from the main game loop and the element we're drawing to. It returns an ID that we can use to cancel the draw. This is useful if our next update completes before this frame is drawn. That's the end of the traditional slideshow, but since we have plenty of time left, I'd like to cover some of our more advanced systems and show you some of our actual code base. Are there any questions so far? Have there been any good questions? No, nothing so far? Okay. So this is the game.js file. And this contains all of the logic for the code. It's only 140 lines, and this includes the onload function, which waits for the page to load. Here it is. Here's the main game loop. So the first part of this is the init function, and this sets up the canvas element, the canvas context, and the game tick, as well as the snowball entity and the mountain entity. And then below that is the run function, which is the main game loop that has date and time logic, as well as the update loop. So this is the actual, like, these three lines are what actually updates the code. So while delta time is less than the game tick, run the update loop, and then subtract the game tick from delta time. And then down here is the code that actually draws everything. So window.cancel animation frame cancels the request if it hasn't been drawn yet. And then if the game isn't paused, run the next animation frame, interpolate that, and then set the last interpolation value to the current one. And then it draws it onto the canvas. So this is what the actual DOM looks like. Oh, by the way, you can actually download all of the source code for this on Microsoft's website. So you can kind of go through each stage, because this is a 4-section presentation. You can go through each of the stages and look at how the code progresses as we add new systems to it. So this section of code is the DOM, and here's the head, which just includes a style sheet that we're using. And this is all of the container elements. So the container with the canvas and the snowball, and then each of the scripts is attached below those so that the page loads before it loads in all the scripts. And there's one other thing that we didn't really cover in that presentation, but you're going to cover in the next, and that is the way entities and the mountain and snowball work. So, let me see if I can actually get this other slide working, because there are some really cool systems that we built into Yeti Bowl that I would like to show off. Alright, I'm going to go ahead and just show you this instead. So this is an overview of the DOM itself and what's drawn by each aspect of the browser. So the canvas is drawing the Yeti, the hiker, the snowball, and the mountain. The UI, which I believe is also in the DOM, is the flag count, the score button, and the input buttons. This is, like, by far the best part of building a game in HTML5. When you're building games in traditional methods, the UI is always extremely, like, time-consuming, frustrating, like getting the mouse clicks, making sure like everything is laid out properly. But with an HTML5 game, you have the power of the browser just right in your hands. So it's just like building a website, basically. Like, you can add buttons, you can position them really easily. All of these input buttons are being drawn by the DOM. The arrows and the snowball have different states built into them. So you've got like the hover events and the on-click events. It is by far my favorite part of game development in HTML5. And finally, the sky is drawn as a part of the background of the website. So like, you could set the body image to the background of your game if it's not updated very frequently. We use a frame wrapper in Yeti Bowl, which is sort of custom code. Previously we worked in Impact.js, which is a game engine for HTML5, and one of our favorite parts of it were these, when we were there, we also built this kind of custom frame wrapper, and that was the first time we used this this logic, and we've been kind of reusing it in every HTML5 game we built since then. So the frame class is a class we build to crop down an image. So if you load a sprite sheet, which John's going to be talking about in the next section, you can't just render the entire image to the screen. You want to render only a subsection of that image. So the frame class allows us to take an image source and break it down into smaller components. That way you're only loading one image file, which means the game itself is loading faster, but then you are cropping it down so that you can animate through it. And this frame has 6 different parameters: the draw position for both X and Y, what HTML image you're using, the angle. So this isn't built in. This was another reason we added the frame class. Having an angle means that you can rotate your entities, like the snowball when it's rolling down the hill. The draw flip, which I'm forgetting now what that does, and the scale, which allows you to scale images up and down. Oh, right. The draw flipped allows us to flip the hikers back and forth as they're going up the mountain. So they face one direction going one way, and they face the other when they're going right. Another thing that's like not just a component of HTML5 games, but all games in general, is state machines. So our entities in the game, like our hikers and the Yeti and the snowball, all have a state that represents what they're currently doing. So a hiker might be sort of idling if it's at the bottom of the mountain, or it might be walking in the walking state when it's going up the mountain, or when it's at the very top and it seals one of your flags, it's in like the victory state, where it's cheering and celebration. And the next slide shows an example of that state machine. So we switch between a loading state, a normal state, the struck state when the hiker is hit by the snowball, and a win and game over state. So I think both of those, the win and game over states, are both the celebration states. And notice that during the update's pretty short, and the switch statement hands off to another function. So like if it's loading, it gets handed off to the loading function. And this means that like your update loops are really clean, and all of your logic is handled in another method within your class. So that's the state machine for the hiker. And state machines are just integral for game entities, especially the player. Like your player can have a really complex state machine, because like it might be jumping, running, attacking, dodging, sliding. Like you can do everything with the state machine, really. The last like major thing is interpolation. So this, so in a normal situation where you have a game update loop that just fires off as soon as you get them, you don't have to worry about interpolation. We use interpolation in our HTML5 games because it means that we can do the fixed intervals in the game engine. So what interpolation does is, in between each update loop, the draw code figures out how far in between the drawing should be. So if your hiker in one frame is at position 100 and the next frame is at position 200, in between there it puts it at 150. And that way it can kind of move things around the screen naturally without running the update code. And like if you remember in the update loop, there was the interpolation value. This is the percentage of time in between each tick, and that's how it calculates how much position the entity moved in between both of the draw calls. That's the entirety of our presentation for now. Unless there's like any questions you want answered before the next slide deck. Right. Well, after a short break, we'll be back with more content. We're going to go to a break, and we'll be right back.